And in order, the way we got the size to decrease is by using hydrofluoric acid and nitric acid, and it would eat at the particles to reduce its size. And then after that, we did functionalization, which is, after etching, this is the end product. As you can see, these H's are on the outside, and as I said before, these are hydrophobic. So in order to make it a little more hydrophilic, we attach it to a compound called semipolar undecyclinic acid in the process called functionalization. And we do this under reflux, and we use this apparatus. This is a 3-neck flask, and and we basically heat up a mixture of the silicon quantum dots, the undecyclinic acid, and ethanol up to 80 degrees Celsius under an argon environment. So after that's done, we get a clear solution with photoluminescence and nonpolar solvent. The reason why it's nonpolar is because of these carbon chains right here. Then the next step is chitosan encapsulation. This is the result that we got from functionalization and reflux. And next, we encapsulate the undecyclinic acid and silicon quantum dots with chitosan to make chitosan-coated silicon quantum dots. And this is the result, and it's more water soluble. So these are the results. After we got the silicon quantum, the chitosan-coated silicon quantum dots, we measured its absorbance versus its wavelength. These two lines here, the red line is the chitosan-coated quantum dots, and the blue line is the uncoated silicon quantum dots. And we saw that there was a very small shift in the peak wavelengths of both of these types of quantum dots, which basically means that although which is a good thing, because once we didn't want to compromise any of its other beneficial properties, such as, for example, the photoluminescence. The next thing we measured was its photoluminescence under different simulated biological environments, such as temperature and pH value. So in this graph, we see that as temperature increases, the photoluminescence of the quantum dots decreases, but at 37 degrees Celsius, which is our normal body temperature, the the quantum dots retain at least 80% of its photoluminescence. And over here, we see that more or less the quantum dots retain their photoluminescence intensity under different pH values. And here is a confocal image under single photon excitation. And the technique in which we got this image was to shine a light at the quantum dots so that it can emit light, which is basically photoluminescence. So this is under a single photon, and what we saw was the light emission over here from the silicon quantum dots, and this is the these little circles over here are called macrophages, which is a type of cell. So, like I said, we see luminescence over here, and this is the cell in which we see the luminescence, and this is the overlay of the two. And then under two-photon excitation, because of the wavelength, and basically with wavelengths, the shorter the wavelength, the more dangerous it is to humans. So what we did was we broke it down into, we used like the total was 900 nanometers, which is a long wavelength, which means it's not that dangerous. So we used 2 photons of that and then got 900 nanometers, which as a result is less toxic for living organisms. And what we got from that was the same thing. We see some light here, and this is the cell in which we see the light, and this is the overlay of the two. So basic benefits of the 2-photon imaging is that it creates a longer wavelength of light excitation, and it allows for deeper penetration of tissue and skin. And this is images, these are TEM images of the silicon quantum dots with undecyanic acid before chitosan encapsulation. Well, you can't really see it, but yeah. And this is the chitosan encapsulated silicon quantum dots, and over here as well. And this is a crystal lattice. And the mean diameter was 180 nanometers. And you might think it's big, but this was basically in water, so the size kind of increased it, so it's not so bad. And then one thing we checked was biodegradability under different conditions. And one thing we saw was that chitosan, when it was stored in a fridge underwater, it retained at least 90% of its intensity. And then when it was stored in an incubator under 37 degrees Celsius, which is our body temperature, it retained around 90%. And when it was in a PBS buffer in the incubator, it decreased substantially. And the reason why this decrease is basically a good thing, because we need for the chitosan, we need for the quantum dots to degrade, because if it retains in the body, it's not a good thing. So we basically use, the PBS can be simulated to a bodily fluid. So the fact that it decreases is a good thing. In conclusion, we saw that it had great stability, photostability under physiologically appropriate environments. The chitosan does allow the quantum dots to be water soluble without compromising its beneficial properties. And these results will allow us to use these optimized chitosan-coated silicon quantum dots as suitable replacements for applications such as cellular imaging, cancer diagnostics, and possible clinical human trials. And future research could be functionalization with biological targeting groups and the binding of the chitosan to siRNA for gene delivery. And these are my acknowledgments.